My name is João Casal. I'm the head of R&D of One Global. One Global is the brand that had the name of TruePhone 2 weeks ago. So we rebranded recently. And I'm here to talk a bit about a way of, or an identification factor that allows to authenticate IoT devices to cloud services using the network standards, cellular network standards. In terms of agenda, first of all, I will focus on the use of a SIM and why it has a unique positioning for IoT cybersecurity. After that, I will just introduce cellular programmable networks and why they allow to act in a security sweet spot. After that, I will present the actual topic, the zero-touch network-based authentication of IoT devices to cloud services. In what regards the SIM or the subscriber identity module, just recalling that it allows to a cellular device to connect to a mobile operator. It is a hardware secure element that we are used to use for over 30 years now. It has computing and storage capabilities, stores quite a lot of private data from phone number, contacts, text messages, but stores as well cryptographic material and unique identifiers like the authentication keys that allow exactly to authenticate the subscriber to the core network. Why it is a security enabler that is proven by billions of devices is actually because it is used by billions of devices for quite some time. As all of us know, all cellular devices have a dedicated hardware, which is the UICC, the hardware that receives the SIM profiles. And these SIM profiles have those informations that I mentioned before that are sensitive as well as security functions. There are statistics that show that by this year, we have around 17 billion devices connected worldwide, which is quite huge. So the SIM is in use by 17 billion devices, which is quite a huge number. That shows exactly that there are no critical failures in the security of this subscriber identity module. And in the future, we believe that in future networks, we believe that new SIM forms will appear and will have new security functions. In fact, I will talk about some of these potential new security functions in the next slides. So the question that I have, so that the entities can think a bit on the SIM, is if it is really secure or it simply doesn't protect anything that is relevant for attackers, the network identifiers. So some questions. If one attacker would compromise a SIM, he or she could, for instance, get mobile internet for free, right? Or selling that mobile internet from the compromised SIM in the black market. It could impersonate a person in phone calls and in SMSs. It could get bank operation confirmation codes from subscriber, for instance, in those calls that we receive by SMS. The attacker could as well access public services, having access to quite a lot of personal information, like personal incomes, family member names, the address of the person. So there is quite a lot of sensitive data that is used or that you can assess by compromising a SIM, or if you would compromise a SIM. So, for instance, if the SIM processes were easy to compromise, mobile operators would not be using it for over 30 years, right? It's obvious. Again, if SIM processes were easy to compromise, to impersonate a person, for instance, lawful interception processes would not be valid. The same, if the SIM processes were easy to compromise, banks would not trust it for its operations. for money transfers, for instance. And the same for governments. If SIMs were easy to compromise, governments would not trust it to authenticate users in the websites from the public services, which happens in Portugal, in fact. So I think that we can accept that the SIM is hard to compromise, right? And some, when I say some, for instance, GSMA claims that it can be used as root of trust. So it is, in fact, a secure element that can be used as root of trust. So looking a bit at the history of the SIM to introduce the eSIM, what we can observe is that since 1991, it is reducing its size, it's reducing the used plastic, but the latest innovation is a radical innovation, right? From the nano SIM to the eSIM, it's a radical innovation. It allows more automation and more security. I will explain why. But it's also relevant to see that in 2022, there was the first eSIM-only iPhone, the 14th. And by this year, in August this year, there were some rumors that Google Pixel 8 could be eSIM-only. And this shows that the big brands are pushing for the eSIM technology. So why the eSIM is evolving towards more security? So if the SIM, the plastic SIM, or the SIM that we are more used to, provides secure identity and stores authentication secrets, being possible to remove it from one device and use it in a different one is questionable, even if we use PIN and PUC codes for security, but these are passwords, and passwords are not the best approaches, right? So being soldered to the board, the eSIM is soldered to the board, ensures that this new form is more secure in the identity of subscribers, because it forces exactly the one-to-one relation between a device and the subscriber. The same happens with the iSIM, which is a different form integrated in the chipset. So looking a bit in the interaction of the SIM versus the interaction on the eSIM to understand why the eSIM fosters automation, this image is exactly from GSMA eSIM white paper, and it shows the interaction of a person with a SIM, which we all know how it goes, right? We go to a store, to an operator, we buy a SIM, we put it in our smartphone and it is connected. But imagine that we need to travel to Australia. We need probably a new SIM, right? Because there is no roaming there that we can use. So we order a new SIM from an Australian operator. We cannot do it online, but it will take some days or weeks to arrive. We receive the SIM, we go to our phone when we arrive Australia, and we change the SIM that we have from that new one, and we are connected. The issue here is that, well, there are manual operations, putting in and out plastic cards and waiting for the plastic card to arrive to our home. So it's not perfect, and it's hard to automate, right? It's almost impossible to automate. In what regards the eSIM, this operation of changing the connectivity provider, first of all, we can buy a connectivity plan by an operator. We can buy it online, and it sends us a QR code that we can scan. And this is the current process of the eSIM. Okay, I'm not saying that it's perfect. It's the current one, and it's the first one. So, but even though we can see that it's completely digital, let's continue then. So we scan the QR code. The operating system, if the smartphone is SIM enabled, asks if we want to download and install the profile. So we are downloading an eSIM profile, and if we answer yes, it downloads and installs profile, and we are connected to the mobile operator. Now imagine the same case that we want to travel to Australia. Again, we go to a website of an operator, we buy a profile, it sends us the QR code, and again, the system asks us if we want to download and install the SIM, and then if we say yes, it asks us if we want to switch. If we want, we switch right away. If not, we can switch after, and it is connected. So, but this shows that the operation is completely digital. So even though this is a consumer operation that has the interaction of the person, right? It is completely digital. So thinking now in IoT, because in fact, up to now, the example was just a consumer example, right? A person interacting with the smartphone for downloading the SIM. The difference in the IoT case is that the SIM profile is pushed from the backend infrastructure to the IoT device and not downloaded to the device by the person, right? By direct operations of the person. And this can be done by several ways. One Global, for instance, has a IoT portal that allows exactly to manage the devices of a given entity, of a given solution provider. And that has the capacity of pushing the SIM profiles to the devices that the person wants. And what's the relevance of this? Imagine, for instance, this news that states that smart hospitals are projected to deploy more than 7 million connected devices by 2026. Imagine the case of an hospital that has 100 devices to deploy and that wants to deploy it with, for instance, a SIM. And what are the differences on deploying the same solution with an eSIM in terms of complexity, in terms of costs, of having people pushing plastic cards to devices, and the velocity of doing that? Because in fact, in that IoT portal that I mentioned that One Global has, it's just a matter of one click. If the solution provider wants to change the profiles, connectivity profiles of all of its devices. So this is quite drastically the deployment of solutions, of IoT solutions that require connectivity. So this is quite relevant when we talk about complexity, costs, and velocity. Now imagine a second case of a smart factory with hundreds of devices. And imagine in this case, the SIM versus Wi-Fi. Imagine that the operator that is configuring the Wi-Fi for the smart factory needs to put the password in all of the devices, and sometimes it fails because it mistakes the password or something like that. And in this case, we can discuss benefits in terms of complexity, in terms of costs, velocity, and as well of security. And in the case of a smart factory, this is quite relevant, right? Because most smart factory solutions, when they are to be deployed, they aim to be as automated as possible, right? So the SIM helps in that sense. Moving a bit further in what regards future applications of SIM technology, as I mentioned before, in future networks, probably the SIMs continue to be there, but with more security functions. We have GSMA IoT Safe, which in fact allows to perform some ship-to-cloud security. And in this case, IoT Safe proposes to use the SIM as a mini crypto safe inside the device, which you can see the structure there. I will not go through it because otherwise I would not have the time to present everything that I have. But it proposes to use the SIM to establish, for instance, a DTLS session between the device and the application cloud server. That's why they have those slogan of being shipped to cloud security, okay? Because it allows to build the secure channel between the device and the server. It's compatible with all SIM form factors, the ones that I described before. It provides as well a common API to interacting with the SIM for a client application leaving that device to interact with the SIM and to use it as root of trust by IoT devices. And it helps to solve the challenge of provisioning millions of devices, which is a huge challenge if you want to provide, for instance, in what regards authentication that we will talk right away, if we want to provide millions or thousands of certificates to a device. So IoT Safe allows to accelerate that. This is the overall architecture. In the left, you can see the interaction with the SIM, with that common API that I mentioned that IoT Safe tries to standardize, that allows exactly the communication between the IoT client application and the security applet in the SIM. Then in the backend side, there is the IoT server application that allows for the functionality of the system, the server middleware that allows the DTLS connection, and then there is the security service that allows to interact with the SIM itself through the SIM OTA, over-the-air services. This allows exactly the mutual DTLS authentication to a server. IoT devices are, in this case, can compute shared secrets in the SIM and keep long-term keys secret because these secrets are already generated in the SIM. The secure element that we agreed that was hard to tamper, right? So if the secrets are generated in the SIM, it's likely that they are secure for long-term use. And the provisioning of credentials, as I said, from a remote IoT security service, it's also possible here. Moving very fast to a second hypothesis being worked at GSMA, which is the security applications for mobile. In fact, what this working group is working at is in pairing mobile applications from mobile devices with applets that run in the SIM. This is quite relevant for several use cases, namely for banking application, transport applications, identity applications. Imagine that you can use that secure element that we agreed that is hard to tamper for keeping secrets from applications that we use that has quite private data, data that we want to keep secure. So this is quite promising. It's in fact a working group that is starting its work, but in the future networks, it's likely that we have more security functions. That is the point that I would like to excel here. So in terms of summary, why DSIM has a unique positioning for IoT cybersecurity? Because it's a proven secure element used by billions of devices already for security functions. DSIM builds on the older brothers, the plastic cards, by adding automation and security through the digitization of the process. And standardization, namely by GSMA, is paving the way to new security functions on the future SIMs. Okay. So moving a bit further for introducing why cellular programmable networks act in a security sweet spot, and in fact I will go quite fast so that we can jump to the topic and relate all of this. Just an overall view over cellular networks. We have the devices, right, that communicate through radio access networks, and they want to communicate to the internet, right, with other public or private networks. The point is that in the middle, we have what we call the core network or backbone network that has quite a lot of functions. These functions interconnect different subnetworks, can be functions of controlling the calls, the authentication functions that communicate with the SIM to authenticate the subscriber, policy and charging functions, and quite a lot of more of them. So my point is that between the devices and the core network, we can assume that the communication is trustworthy. Why? Because it uses licensed spectrum. It has that security imposed by the subscriber identity modules, the confidentiality of the communication, the encryption, and the security standards that are employed there. Between the core network and the public internet is what we can assume as to be untrustworthy, right? Threats from unknown networks are common, cloud services that we don't know, and devices that we don't know. Usually the threats come from that side of the network to the middle, right? And in this case, what I would argue is that the core network is a cybersecurity sweet spot in the intersection of the trustworthy and with untrustworthy zone, because up to there, from the devices to that core network, we can assume that is trustworthy, and from that there on, it's untrustworthy. So if we want to apply measures of protection, this is a security sweet spot, right? Moving a bit further, and just one slide on the introduction of programmable networks, which is not a new concept, right? And exactly to introduce why we are applying authentication or identity servers living in the core network. Computer networks, as we know, are complex and difficult to manage. There are many components that are still configured manually by network operators, and this approach obviously slows down innovation, increases complexity and costs on running a network. However, there are paradigms that most of you surely know, at least as well as myself, like network function virtualization and software-defined networks that focus exactly on virtualizing the network components and controlling them and the traffic via software and standardized APIs. And in fact, this fosters network automation, less complexity on the integration of new components, and innovation. So why programmable networks are relevant for network-based cybersecurity? Because it fosters automation and reduced human intervention. Because an API-driven network simplify and accelerate the integration of new cybersecurity tools, and because it acts in that security sweet spot, and communication control allows exactly to face most of the cyber threats that depend on communication channels to achieve their goals. Moving to the zero-touch network-based authentication that builds upon everything that I said before of these IoT devices to cloud services. So the problem is that IoT authentication in cloud is still hard. There are credential provisioning that is challenging because it happens in manufacturing time. It's costly, it's hard to scale. Imagine, for instance, the need to connect proprietary hardware to provide credentials to any hardware that you have in the device. This is costly, this takes time, and this doesn't scale, right? Also, hard-coded username passwords are well accepted as bad practices, but are still used quite a lot. So the solution that we propose, in this case, as a third authentication factor, building on the previous two that Atos and UWS explained before, is to leverage the cellular authentication and the SIM credentials already stored in hardware secure element to authenticate IoT devices to cloud services. And this diagram, with this diagram, I will try to explain how this works. In the far left, you can see the IoT device that is able to authenticate to the core network. The core network is that layer in the middle. Having this, and please recall that the communication between the devices and the core network we can assume as trustworthy, as secure, right? The device is then, after that authentication in the core network, the device is able to request a new service that we are building in Arcadian, request that device to provide an ID token, a secure, protected ID token, for authenticating in a third-party service in a cloud provider. So what this process in the core network does is it will verify in the databases, the subscriber databases, if that device was able to authenticate, so it's a known subscriber, and if so, it will issue a protected network ID token that is possible to be verified in the cloud service. This is the process that we propose. And in fact, this process, as far as we understand, is quite lightweight. No new cryptographic material is needed. just the SIM secrets and processes. No new hardware is needed, so just the SIM, any SIM form. In fact, eSIM it's possible. It has the advantages that I mentioned before, but it works with any SIM form. It leverages proven security standards that we accept as secure, right? We use it. All of us use our mobile phones for banking, for instance. So we accept that the SIM is likely to be secure. And it's scalable. So no added effort on IoT device manufacturing time, other than putting the SIM there, right? And putting the SIM profile in the SIM. Different approach that we just published, or that we are publishing in a workshop, a paper that has been accepted, is the following one. And this allows to authenticate very, very constrained devices. I will go fast because I know that my time is running out. But the idea is that this image that you can see is similar to the previous one, with the difference that the token returns to the device. So in the step one that you can see between the client and the identity server that we call notarizer that lives in the core network, the client requests the identity token. The notarizer verifies if it is a valid subscriber. If so, it returns the identity token. That identity token in the step 3 is sent to the third-party cloud service that may verify the validity of the token in the identity server that lives in the core network, or verify it itself as it was in the previous image, and then grant the access to the service to the client. In this case, you can see that we use HTTP in steps 1 and 2, and the reason for that, HTTP as a non-secure protocol, let's assume that way. The reason for that is exactly because the connection between the client and network server, the core network is secure, as we discussed before. After that, we use MTTS, which is more secure, right? But it's also demanding, so it's not very appropriate for very constrained devices. And the reason that we had, or the challenge or the motivation that we had for this work, was exactly to try to reduce the effort of the client to the bare minimum. And for what we did was to build a broker in the core network that in fact allows the client to use a constrained protocol, okay, a protocol that is applicable to constrained devices, and request that broker to communicate with a third-party cloud service, and it will rely on it for that communication. So the broker, in this case, what we'll do is to translate the protocol to a more secure protocol that will depend on the third-party cloud service, but that will not increase the effort in the client side. And the broker will as well attach to that payload that the client wants to communicate the identity of the client itself. So it pushes the payload to the third-party service and identifies the client as well. So in this case, we could achieve, in terms of network traffic, over 90% of reduction, which shows less effort in the client side. And this can be applied by trusting that the core network is secure, and by trusting the core network itself. So to finalize, last slide, why to use network-based authentication of IoT devices to cloud services? First, it overcomes common challenges related with passwords, right? Weak or hard-coded passwords, with credential provisioning as well, in terms of scalability, with the lack of physical hardening, because it uses the SIM, the credentials that are in the SIM, and the SIM technologies we know, and as we discussed before, are already critical and trusted in nowadays cybersecurity, trusted by telecom operators, governments, banks, and by ourselves. And the trust in the communication between the devices and the core network allows exactly to have very lightweight authentication proven as secure.